It is April 30th, 2026. Inside the MIT Academy of Engineering Laboratory, the atmosphere is quiet and focused. Across the room, teams make last-minute adjustments to mechanical prototypes and run diagnostic checks on their laptops. The machine dynamics exam requires students to take the predictable mathematics of the classroom and apply them to the chaotic physical forces of real hardware. To pass, these teams must demonstrate mastery over the core syllabus, identifying free and forced vibrations, balancing high-speed rotating masses, and calculating dynamic forces. Every theoretical equation and computer simulation built over the semester is about to be physically tested. The numbers on the screen must accurately predict the behavior of the hardware on the desk. One student group is presenting a comparative dynamic analysis of different bicycle suspension configurations to measure rider comfort. This diagram shows the 2DOF lumped parameter model. The bicycle is represented as ideal springs, dampers, and rigid boxes. The rider and main frame become the sprung mass, while the wheels and fork represent the unsprung mass, taking the direct road impact. This schematic illustrates the complexity of a full suspension design. Using MATLAB, the students simulated these interconnected masses under continuous road excitation. By mapping transmission paths, the team pinpoints when road frequency matches the bicycle's natural frequency, designing against resonance. Turning physical frames into equivalent math matrices gives engineers the power to tune mechanical components before a single part is manufactured. It allows them to isolate the passenger from the road through software. While one team models a bicycle, another applies the same physics to a massive 30,000-kilogram railway bogie system. This schematic visualizes the track irregularities pushing upward into the train. The students used Python to write coupled differential equations, creating a digital filter to smooth out that energy. Their results prove that the secondary suspension acts as an energy barrier. When properly tuned, this stage physically blocks high-frequency bogie vibrations from reaching the passenger cabin. Large-scale software simulations sit adjacent to physical hardware projects. Other teams are working with high-speed rotating machinery right on the lab benches. This group built an IoT-based condition monitoring prototype. The microcontroller reads physical vibrations from the motor's rotation and translates them into real-time digital diagnostic signals. Whether simulating a massive train or wiring a tiny motor, the core engineering objective remains identical. Engineers must predict and control dynamic forces before they cause mechanical failure. As the morning preparation ends, the internal and external examiners step up to the benches to begin the formal viva. The faculty review the hardware and scrutinize the computational code. Students are now expected to explain the reasoning behind their design choices. The questioning is technical. Students must orally justify their mathematical outputs, explaining exactly what their frequency response functions and transmissibility plots mean for the hardware. Beyond the functional hardware, examiners test the students' ability to explain the specific physics of vibration isolation. A working model is the baseline. The real test is the defense of the theory. Surviving this technical defense requires absolute confidence in the math. It proves a student's ability to stand by their technical decision-making under expert scrutiny. By the end of the afternoon, the tension breaks. Prototypes are powered down and laptops are closed as the teams pack up their workbenches. They have successfully navigated the core challenge of machine dynamics, learning to tame chaotic physical forces to ensure mechanical stability. Through heavy computation and hardware testing, this cohort proved they can bridge the gap between textbook equations and industrial diagnostics. These students are now entering the industrial landscape. Today's demonstrations mark their final transition into the mechanical engineering class of 2026.